Let's talk about where in the brain memory is happening. And of course, there's a variety of structures involved in this, but when we're talking about laying down new long term memories, there's actually one structure that has consistently been found to be really, really critical for long term memory formation. And that structure is the hippocampus. You see here an image of the hippocampus, a three-dimensional image, but the location of the hippocampus is kind of deep in the midbrain, right over here, and very close to another well-known structure called the amygdala, which is involved in a lot of emotional processing. And we'll talk about that area more later in the course. So how do we know this? Well, we know this from different kinds of what's called amnesia. And amnesia is a word for memory loss. So amnesia comes in different forms, but as an umbrella term refers to selective disruption of the processes underlying long-term memory, meaning that typically speaking, amnesia does not involve short-term memory or sensory memory. It's specifically about problems with long-term memory. And it could be either about long-term memory formation or about pulling information out of long-term memory. What's interesting about people suffering from amnesia is that typically other cognitive functions are not impaired. So in other words, their intelligence isn't really been altered, their attention isn't really been altered. It's quite specifically about creating new long-term memories and retrieving old long-term memories. Now, if you think about those two different directions in which memory loss can work, there's, as I already said, two different ways in which this can go. You can either suffer from loss of information that was learned before you had some onset of amnesia, and that is called retrograde amnesia. Retro, just think backwards, so in other words, backwards working in time. You have an event that leads to brain damage, and retrograde amnesia means that there's memory loss from before that event. You can also suffer from anterograde amnesia, and antero meaning forward working. And anterograde amnesia is really about the inability to learn new information after onset of amnesia. So that's really about storing new long-term memories. And typically, and very unfortunately, in most patients with amnesia, they have at least some of both of those forms. How do we know what we know about where this happens in the brain? As is so often the case, there is a landmark case that really established the role of the hippocampus in long-term memory, and that's the case of HM. And HM was a patient suffering from epileptic seizures, and in order to treat that, in the 1950s, they would actually do a lobotomy where they would remove part of the temporal lobe, and in his case they removed also part of the hippocampus and the amygdala, in order to try to stop those seizures. This seems like a really bad idea now, but keep in mind that they didn't know as much about the brain as we do nowadays. So what happened after that surgery? Well, HM did in fact experience a reduction in the severity of his seizures, but unfortunately became severely amnesic. And here is some images, a coronal slice, this is called, because it goes right through the middle of the brain. You see here the ventricles, and you see here gaping holes, these black areas right here, which is the location where the hippocampus would normally speaking be, but in the case of HM, those areas were cut out. And this is just some slices that are further towards the back of the brain, towards the front of the brain. Now, what do we know about exactly the nature of impairment that HM suffered from these lesions? Well, first of all, we can look at the primacy and the recency effect, and we've already talked about this. The primacy and recency effect are both part of the serial position curve, where people get a list of different words to remember, say 10 or so, and then we look at how well they can remember a word depending on its placement in that word list. And what we saw there already is that the first couple of words are remembered better, and that's called the primacy effect, and that's been linked to long-term memory. And the last couple of words are remembered better. That's called the recency effect, and it's related to short-term memory. Well, interestingly enough, when HM does a serial position recall task, he gets a wipeout of the long-term memory effect, while the short-term memory effect is still in place. So the recency effect is there, but the primacy effect is actually completely gone. What exactly did HM experience? Well, he had severe anterograde amnesia, meaning a complete inability to form new memories. And what this suggests is a deficit in encoding, meaning laying down new memories. And you can see this in this graph. If you look at relatively how much memory was present in HM's stories compared to the time of the procedure, he had the operation in 1953, and you see that there were basically no new long-term memories formed after that. So that is anterograde amnesia, forward working. But he also had definitely some impairment in retrograde amnesia, in the sense that some of his memories from the several years before the actual surgery were also not quite as good as memory from his childhood. And this really expressed itself in really, really devastating ways for HM when you looked at his daily life. So, for example, he was able to recall childhood memories, but the memories from the 3 years prior to the surgery became spotty. And initially, it was thought that he really couldn't actually form any new memories at all. And it turned out that this was really quite devastating. So, for example, at some point, HM's father had passed away. And every time HM was reminded of this or told this, this was a new experience for him, and it was as if his father had just died all over again. In terms of his job, he couldn't remember what his job was or describe what his job was supposed to be. And the most striking part of this, I find, that he worked with the same doctor for years on end, and every single day that that doctor came into the room, he would introduce herself to her as if he had actually never met any of those doctors. So that's pretty severe impairment. Now, was the impairment across the board for long-term memories, however? Well, it turns out that that's not exactly the case. But we'll get to that in 1 second. Let me first say a tiny bit more about the impairments in his long-term memory and why we think his short-term memory was actually intact. So what we can do with HM is, of course, subject this person to a battery of tests, that some of which we've already talked about in this course, and one of them is the digit span test. And in that test, again, you were given 5 digits, read at 1 second intervals, and if you get 5 correct, then on the next trial you get the same 5 and an additional 6th one. If you get that correct, you get a 7th one. If you get that correct, you get an 8th one, and so forth. Now, interestingly enough, after 25 trials, HM never got past 7 correct digits. And that's interesting because we've seen that number 7 before. It's actually linked to the capacity of our short-term memory. Most people, if they get 25 trials, can actually learn, well, maybe they need a little more than 25 trials, but they can actually learn up to 18 digits. Because if you do this over and over, these digits start to be transferred to your long-term memory, and this becomes, rather than a short-term memory task, this becomes a long-term memory task. But it's significant that for HM, the limit was 7, which is exactly the limit that we've seen of short-term memory. So this suggests that really HM did not have a working long-term memory capacity to do this task. Was this completely across the board though? Turns out it was not, and I'm going to post a video of a task that was used on HM, which is called the mirror drawing task. To just describe this first, this is a task where people are seeing their own hand in a mirror, and while they see their hand and they hold a pen in that hand, but they're blocked from direct vision of their hand, so they can only see their own hand in the mirror. They are then told that they need to trace a star as accurately as possible without going outside of the lines. And this is a difficult task that people can pretty quickly learn after some training, but it's difficult because it requires kind of a remapping between what you see your hand doing versus the direction in which your hand is moving. So as your hand moves to the right, it looks like, because of the mirror, as if it's moving to the left, and vice versa. So it takes people a while to get better at this, but they can certainly do this. Interestingly enough, HM also was able to get better and better at this. And let me just show you this. So if you look at the number of errors per attempt, right? So the more errors you have, the worse you do. And then over the days of training, you see that originally people get better very quickly. And then on day 2, right, they take a break and they continue on day 2, and they're still actually quite a lot better. And on day 3, they're pretty much really decent at doing this. Now, it turns out that HM's learning curve looked exactly like this, just like any other participant. So apparently, HM was able to learn this long-term memory skill. And the salient thing about it was that every day that he started doing this task, he would actually emphatically claim that he had never ever done this task before. So he had no recollection of the event of doing the task. He had no recollections of the doctors involved in helping him do the task. But yet his long-term memory system for skill learning, the implicit procedural memory system, was actually still intact. So that was really interesting and important because it really gave rise to a much more refined theory of what long-term memory is and what parts of the brain are involved in it. So first of all, his case really established the involvement of what's called the mediotemporal lobe in memory, or in other words, the hippocampus. Before that, we were not quite as acutely aware of how important that area actually is for memory encoding and for laying down long-term memories. The other thing that HM's case did at the time was that it really challenged the view that memory functions were equivalently distributed throughout the brain. So what that means in simple language is that until that time, neuroscientists had thought that the entire brain was involved in memory, and that sort of, it didn't really matter where in the brain you were. Some of it was always involved in some sort of memory structure, and there was not really any specific structure that was actually helping with encoding new long-term memories. Well, the case of HN really challenged that view because the removal of the hippocampus really turned out to be the critical part, and that particular structure is really what is absolutely required in order to lay down long-term declarative memories. It's also a clear case of, again, a separation between short-term memory and long-term memory. So I described several findings and patterns of results with HM where he clearly had a short-term memory. He could learn up to 7 digits. He would have a recency effect in the serial positioning curve. But the long-term memory effects, such as the primacy effect, were really the ones that were impacted. And the key thing here to end this is that the mediotemporal lobes are really very, very critical when it comes to memory consolidation. So specifically the hippocampus. Hippocampus is critical for consolidation in long-term memory, and what's interesting about that is that it's astonishing that infants and young toddlers, as they grow up, right, we as adults, have virtually no memories from the first 4 or so years of our lives. Why is that? Well, it's well known that as infants are born, if you take a scan of their brain, their hippocampi are especially underdeveloped. So they're not fully developed yet at birth. And in those first 5 years, the hippocampus is actually an area that goes through pretty dramatic development. And that's sort of the point at which people start forming enduring long-term memory. So it's another indication that the hippocampus is a really critical structure, that you have to have a matured hippocampus in order to lay down long-term memories. What's interesting too is that if you look at older people, on the other hand, oftentimes when they have trouble with explicit memory, if you then do a brain scan or after they die you can perform an autopsy, you can actually see that they typically have either cell death going on in that area or they have some sort of disease going on in the neurons, and specifically again in that hippocampus. So the hippocampus is just a very, very fundamental structure when it comes to memory formation.